Hello AP Calculus people, this is Mr. McAllen again, and we're going to be working on the lamppost problem. So what I'd like you to do is I'd like you to read the problem about the lamppost and try drawing a diagram that represents all of the given information. I'm going to pause the video, and when we come back, I'm going to draw it with you. But first you try to draw it yourself, and let's see if our drawings and labeling coincide. Okay guys, here we are, and we have a lamppost that's 20 feet tall, and we have a person that is 6.5 feet, and it casts a shadow. I think I just switched the orientation of my video by accident, so here we go, we're back again, and some strange things happened there, so let's just see what's going on. So we have we basically can see we have a triangle where we have, the person standing here, and we have their height and the lamppost height, and we should label some of these diagrams. So this is 10 feet, and because that's the distance that Evan is standing away from the lamppost, I'm going to label this distance to be E for Evan, and I'm going to label the rate at which he walks away to be dE dt. And then we have the distance of the shadow, and the distance of the shadow, you can consider that to be this distance. We'll just call that S, and I'm going to call that this ds dt. And now what I want to do is I want to calculate what ds dt is from the problem. So I'm going to pause the video, and I'd like you to try to come up with the relationships that you see in the picture that deal with E, S, ds dt, and dE dt. Okay, so we're back, and we're talking about the lamppost problem, and one of the things that you have to look at when you see this picture is, the tough thing is knowing what to do with it. What I see is a set of similar triangles, so I'm going to draw the similar triangles, and hopefully we'll see the meaning in the problem at that point. So this is E. This distance from here to here, the distance from Evan is from the lamppost, and this distance is the length of the shadow. Using similar triangles and the dimensions of the height, we can set up where we know we can calculate how E and S relate to each other. So in the first figure, this is S and this is 6.5. In the second triangle, we have 20 and E plus S. So we can set up a proportion, and as long as the proportion relates the quantities that we're interested in, we can use related rates. So we're going to end up having this equation when we cross multiply of 6.5e plus s equals 20s. When we simplify this, we get 6.5e plus 6.5s equals 20s. We come up with a simple linear equation of how E relates to S. And guess what we do at this point? We would take a time-based derivative, so we'd have 6.5 dE dt, which is the rate at which Evan moves, is equal to 13.5 times ds dt. And when we solve for dSdt, because we know how fast Evan's moving, we have 6.5 divided by 13.5 times Evan's rate of movement. Since Evan is moving at 10, let me just double check what his, he's moving at 1 foot per second. We can just solve for dSdt, and that is equal to the quotient of 6.5 divided by 13.5 feet per second. Hopefully this problem has helped you understand how to do the shadow problem. It's really that simple, but what a lot of people forget to do is to consider similar triangles. So similar triangles is the key to solving the shadow problem. Please like or comment on this video if you want to see more, or subscribe to this channel.